Close your eyes. Imagine the endless night sky dusted with billions of stars. Somewhere out there, deep within the heart of our Milky Way galaxy, lies something unimaginable, a monster whose gravity is so immense that not even light can escape its grasp. Its name is Sagittarius A star. We can't see it, yet we know it's there. It silently directs the celestial dance of hundreds of billions of stars, including our own sun. What mysteries does it hide within its profound darkness? Tonight I invite you on a journey designed to help you relax and fall asleep. We will travel to the most mysterious object in the universe to unlock its secrets. I promise this story will be as mesmerizing as it is deeply calming. Are you ready to discover what lies beyond the event horizon? Before we plunge into the abyss itself, let's take a brief look back. The idea of dark stars, objects so massive that their gravity traps light, first appeared back in the 18th century. But it wasn't until Albert Einstein's general theory of relativity, published in 1915, that we had the theoretical foundation for the existence of black holes. Interestingly, Einstein himself doubted they could truly exist. But the math was relentless. Sagittarius A star was first detected in 1974 by astronomers Bruce Ballack and Robert Brown. It appeared as a compact and exceptionally bright radio source at the Milky Way's core. For decades, scientists gathered evidence by observing stars that orbited this invisible center at incredible speeds. Their orbital paths left no doubt. At the heart of our galaxy resides an object with the mass of about 4 million suns, compressed into an impossibly small volume. This is our supermassive black hole. It lies 27,000 light-years away from us. While that sounds like an immense distance, on the cosmic scale it is in fact our closest neighbor of this kind, and tonight we will delve into its secrets. So what exactly is Sagittarius A star? Let's try to wrap our heads around its sheer scale. Imagine our sun. It's absolutely massive, accounting for 99.86% of the entire solar system's mass. Now multiply that mass by 4,300,000. That's the staggering number of solar masses contained within this single object. All this colossal mass is concentrated in a region of space that could easily fit inside the orbit of Mercury. However, that only describes the extent of its gravitational influence. The singularity itself, the theoretical heart of the black hole, is infinitesimally small. This incredible density creates a gravitational field from which there is no return. The boundary of this region is known as the event horizon. For an object with the mass of Sagittarius A star, the radius of this point of no return, what we call the Schwarzschild radius, is approximately 12 million kilometers. That's about 17 times the radius of the Sun. While that seems enormous for such a massive object, it is surprisingly compact. Orbiting this invisible sphere is a superheated accretion disk, matter, spiraling down into the abyss. It is the glow of this disk, heated to millions of degrees by friction and gravitational compression, that we are able to observe. The black hole itself remains perfectly black, swallowing everything that crosses its boundary. Imagine a massive whirlpool in the ocean. You can clearly see the water swirling around the center, accelerating faster and faster. But the center itself, the actual vortex, plunges into the dark depths. Sagittarius, a star, is exactly like that, a cosmic whirlpool of space-time. And today, we're going to try to peer into its heart. Let's talk more specifically about the event horizon. It's not a physical surface you can touch. It is a mathematical boundary, the ultimate point of no return. Imagine you're on a spaceship heading toward a black hole. To escape the gravity of any object, like Earth, for example, Your ship needs a specific velocity, commonly known as the escape velocity. For Earth, that's just over 11 kilometers per second. As you approach the black hole, that required speed increases exponentially. Right at the event horizon, the escape velocity becomes equal to the speed of light, 300,000 kilometers per second. And since nothing in the universe with mass can move faster than light, once you cross that line, there is simply no going back. You are permanently trapped by gravity. What's fascinating is that if you were falling into a supermassive black hole, such as Sagittarius A star, you wouldn't even notice the exact moment you cross the horizon. The gravitational forces there aren't yet extreme enough to rip your ship apart. You would simply drift through the invisible line, and in that moment your fate would be sealed. However, to an outside observer, everything would look drastically different. As you approached the event horizon, your image would become increasingly red due to gravitational redshift. And from their perspective, your time would slow down almost to a complete stop. They would see you frozen at the boundary, slowly fading away over an eternity, never actually crossing it. Yet in your own frame of reference, you would continue your fall toward the singularity. The event horizon is a boundary not just in space but also in time, splitting the universe into two distinct parts, the region you can return from and the one you can never leave. Let's now turn our attention to what surrounds that darkness, the accretion disk. While the black hole itself remains invisible, its presence generates one of the most luminous and energetic phenomena in the entire cosmos. Sagittarius A star, or SGRA star, by the standards of supermassive black holes, is actually quite docile. It isn't an active quasar relentlessly gorging itself on entire stars, but even its relatively modest accretion disk is home to incredible, violent processes. The disk is made up of gas, dust, and stellar remnants dragged in by the giant's powerful gravity. This material doesn't fall straight into the black hole. Instead, thanks to the conservation of angular momentum, it swirls into a massive, flat structure, often compared to a gigantic vinyl record. The rotation speed of the material within this disk is staggering. Its innermost regions whip around at velocities approaching the speed of light. The immense friction between layers of gas, which are moving at different speeds, causes the material to heat up to millions, sometimes tens of millions, of degrees. This superheated, incandescent gas radiates an incredible amount of energy, primarily visible in the X-ray and radio wavelengths. This intense radiation is what astronomers observe. Furthermore, powerful magnetic fields churn within the accretion disk. These fields twist into gigantic spirals, occasionally channeling and expelling some of the infalling matter away from the black hole in the form of narrow, focused beams called relativistic jets. SGRA star also produces these jets, although they are far less powerful than those seen in active quasars. They shoot out from the black hole's poles and stretch across several light years. Ultimately, a black hole is far more than just a cosmic vacuum cleaner. It acts as a complex engine that converts the gravitational energy of infalling matter into powerful radiation and particle streams. This mechanism profoundly influences the surrounding space and even affects the rate of star formation at the galactic center. One of the most mind-bending predictions of general relativity is the idea that gravity actually warps space-time itself. And next to an object as massive as Sagittarius A star, this effect is on full display. Picture a tightly stretched rubber sheet. If you place a small, light marble on it, it only causes a slight dip. But replace that with a heavy bowling ball and it creates a deep, noticeable well. Massive objects warp the fabric of space-time in exactly the same way. Light traveling past such an object is forced to follow this curved path. This phenomenon is known as gravitational lensing. A black hole is the ultimate gravitational lens. Light from stars lying behind it bends around the singularity from every direction. As a result, we observe a distorted, stretched, or sometimes even multiple images of the same star. If a star is positioned perfectly behind the black hole, its light can form an immaculate ring, an Einstein ring. When astronomers observe the stars near Sagittarius A star, these effects are constantly visible. This isn't just a beautiful sight, it's a powerful tool for studying the properties of the black hole itself and testing general relativity under extreme conditions. What's more, due to this extreme curvature, if you could somehow hover near a black hole and look in just the right direction, you might actually be able to see the back of your own head. Light originating from you would loop around the black hole and return directly to your eyes. This is a world where straight lines curve and space folds back in on itself. This is the reality predicted by Einstein a century ago, now confirmed by observing the invisible giant at the center of our galaxy. We've previously discussed how time flows differently for someone falling into a black hole compared to an observer safely far away. This phenomenon is known as gravitational time dilation, yet another consequence of space-time curvature. The stronger the gravitational field, the slower time progresses. We actually experience this effect, though only to a minuscule degree, right here on Earth. For example, clocks on GPS satellites run slightly faster than those on the planet's surface, a difference crucial to account for to ensure accurate navigation. However, near a black hole, this effect reaches truly mind-boggling proportions. Imagine taking an expedition to Sagittarius A star, that's the black hole at the center of our galaxy. Your friend stays behind on Earth. You orbit the black hole at what seems like a safe distance, but still deep within a strong gravitational field, and your journey lasts, by your personal clock, maybe 1 year. When you finally return to Earth, you would discover that for your friend, not just 1 year has passed, but perhaps 10, 100, or even 1,000 years, depending on how close you got to the event horizon. For you, Earth's entire history would have sped by like a time-lapse film. A journey near a black hole is therefore essentially a one-way trip into the future. You can't return to your own original time, but you can transport yourself into your civilization's distant future. This creates numerous philosophical and practical paradoxes. What if you left a family behind on Earth? You would return only to find that even your distant descendants had vanished. This concept forms the basis of countless science fiction narratives, yet it is crucial to understand that this is not fiction. It is a direct consequence of the laws of physics governing our universe. Time is not absolute. It is relative, and the gravity of a black hole is the most dramatic demonstration of that fact. Now let's turn our attention to a phenomenon that is far less pleasant, but arguably just as fascinating, waiting for any object that strays too close to a black hole. This process goes by the rather humorous name of spaghettification. It occurs due to the immense difference in gravitational strength acting across an object's body. These are known as tidal forces. They are the same forces responsible for the tides we see here on Earth, caused by the gravity of the Moon and Sun. But near a black hole, these forces become utterly monstrous. Imagine a hypothetical astronaut falling feet first into a black hole. His feet are fractionally closer to the center than his head. Because of this, the gravity pulling on his feet is dramatically stronger than the gravity pulling on his head. This difference in force immediately begins to stretch his body. Simultaneously, the gravitational forces acting on his shoulders are pulling inward toward the center, compressing him from the sides. This twin effect results in the astronaut's body being stretched into a long, thin strand, resembling a piece of spaghetti. This process is irreversible and completely destructive. For a stellar mass black hole, one that's only a few times heavier than our Sun, spaghettification would occur before the object even crosses the event horizon. However, the situation is different for a supermassive black hole like Sagittarius A star at the center of our galaxy. Due to its immense size, the curvature of spacetime at the event horizon isn't as severe. The tidal forces there are relatively weak. An astronaut could, therefore, potentially cross the event horizon totally intact. But inevitable spaghettification would await them inside as they spiral closer to the singularity where the gravitational gradient becomes infinite. Astronomers have already observed this phenomenon in action, watching stars that strayed too close to supermassive black holes in other galaxies. They are ripped apart, their stellar material transformed into long streams of gas that are ultimately consumed by the cosmic monster. For a long time, black holes were purely theoretical objects. We could only infer their existence through indirect evidence, by observing the movement of stars circling them, or by detecting the radiation emitted from their accretion disks. But how do you see something that is by definition invisible? How could we possibly capture a direct image of a black hole's shadow set against its superheated surroundings? The challenge seemed insurmountable. To resolve an object the size of an orange on the moon, we would need a telescope the size of planet Earth. And that seemingly impossible idea was finally brought to life by the project called the Event Horizon Telescope, or EHT. The EHT isn't a single instrument. It's a global network of radio telescopes scattered across the entire planet, from Chile and Hawaii to Antarctica and Spain. Working together, synchronized by atomic clocks, they effectively create a virtual telescope the size of our planet. This technique is known as very long baseline interferometry. In April 2019, the EHT team stunned the world by unveiling the first ever image of a black hole. This was the shadow of the supermassive black hole at the center of the Messier 87 galaxy, a behemoth 6.5 billion times more massive than our Sun. What we saw was a dark, central region, the very shadow cast by the event horizon, surrounded by a bright, asymmetrical ring of light from superheated gas. It was a triumphant confirmation of Einstein's predictions. Astrophysics had officially shifted from the realm of theoretical calculation into the era of direct observation. The entire world is now waiting for the EHT to show us the portrait of our own black hole, Sagittarius A star. And so in May of 2022, it finally happened. The Event Horizon Telescope team unveiled the first image of Sagittarius A star. Why did this take so much longer than M87? Although Sagittarius A star is much closer to us, it is also significantly smaller. Its mass is 1,000 times less than the behemoth in M87. This means the gas in its accretion disk rotates far more rapidly. While M87's matter completes one orbit in days or weeks, the material around SGR A star circles the black hole in a matter of minutes. It's the equivalent of trying to photograph a quickly running puppy. The image is constantly blurred. Scientists had to develop new, far more complex data processing algorithms to assemble a clear picture from this chaotic flickering. And they succeeded. In the image, we once again saw the dark center, the black hole's shadow, encircled by three bright clumps of superheated gas, rotating around it at nearly the speed of light. The size of the shadow precisely matched the predictions of general relativity for a black hole weighing 4 million suns. This provided undeniable evidence that a supermassive black hole truly sits at the center of our galaxy. This image is not just a beautiful picture, it is a map of the gravitational field under the most extreme conditions imaginable. By analyzing the ring's shape and brightness, scientists can study the properties of the accretion disk, measure the black hole's spin rate, and look for any deviations from Einstein's theory that might hint at new physics. This is a window into the very heart of the Milky Way, opened through the genius of scientists and a modern technological marvel. One of the most compelling proofs for the existence of Sagittarius A star, SGR-A star, established long before the Event Horizon Telescope Project, EHT, came from observations of the so-called S stars. This is a cluster of stars orbiting the galactic center at extremely close proximity and immense speeds. Studying them became a genuine astronomical saga, earning its principal researchers, Reinhard Genzel and Andrea Ghez, the Nobel Prize in Physics in 2020. For nearly 30 years, two independent teams of astronomers, one in Europe and one in the US, used the most powerful telescopes on Earth to track the movement of these stars, pixel by painstaking pixel. This was an unbelievably complex undertaking. The galactic center is hidden from our view by dense clouds of dust, requiring observations to be made exclusively in the infrared spectrum. Furthermore, extreme precision was necessary just to distinguish individual stars in this incredibly crowded region. The scientists employed adaptive optics technology, which compensates for the distortions caused by Earth's atmosphere, resulting in incredibly sharp images. Year after year, they mapped the trajectories of these stars, and what they observed was astonishing. The stars followed perfect elliptical orbits, precisely in line with Kepler's laws, revolving around empty space. There was nothing visible there, yet something was forcing these stars to race at thousands of kilometers per second. Star S2 was a particular standout. It completes a full orbit around the center in just 16 years, approaching it to a distance of only 120 astronomical units, AU, roughly 4 times farther than Neptune is from the Sun. At its closest approach, its speed reaches nearly 3% of the speed of light. Studying the orbit of the S2 star has proven to be a veritable goldmine for physicists. By tracking its complete revolution, astronomers were able to calculate the mass of the central object with astonishing precision. The numbers aligned perfectly, approximately 4 million times the mass of the Sun. Since this entire object had to be contained within the S2 star's orbit, its density had to be colossal. No known star cluster or cloud of gas could be both that massive and that compact simultaneously. The only possible explanation was a supermassive black hole. But that was only the beginning. In 2018, the S2 star made another close pass to the black hole. This time, scientists were ready to test yet another prediction of general relativity, gravitational redshift. According to the theory, light escaping a strong gravitational field should lose energy, causing its wavelength to shift toward the red end of the spectrum. And that is precisely what they recorded. The spectrum of light from S2 shifted by exactly the amount Einstein's theory predicted for an object making such a close approach to a black hole of that enormous mass. It was yet another brilliant confirmation of the great physicist's accuracy. Observations of the S stars provide a perfect example of how patient, painstaking work spanning decades can lead to truly fundamental discoveries. This allowed us not only to successfully weigh our invisible cosmic monster, but also to utilize it as a gigantic laboratory for testing the laws of the universe under the most extreme conditions imaginable. Let's turn now to the biggest question of all. What exactly is inside a black hole? What mysteries are hidden beyond the event horizon? The answer, unfortunately, is both disappointing and deeply intriguing. We simply don't know, and perhaps we never will. The core problem is that the event horizon acts as a perfect informational barrier. No signal, no particle, and absolutely no data can escape its boundaries and reach us. Everything we theorize about the black hole's interior is based entirely on theoretical models that could very well be wrong. According to classical general relativity, at the very center of the black hole lies a singularity. This is defined as a point of zero volume and infinite density, where the curvature of space-time becomes boundless. At this point, all the known laws of physics break down. The very concepts of space and time lose all meaning. However, most physicists agree that the singularity isn't a true physical object. Rather, it's a sign that our current theory is incomplete. General relativity expertly describes gravity on vast scales, but it fails to account for the effects of quantum mechanics, which must become dominant under such extreme conditions. What we need is a theory of quantum gravity, a unified theory that could finally merge these two great breakthroughs of the 20th century. But as of now, that theory remains elusive. We do have several strong candidates, such as string theory or loop quantum gravity, and each offers its own unique predictions about what happens at the black hole's core. Perhaps there is no infinite point at all, but instead some kind of exotic object, for instance, a Planck star, a clump of matter compressed to an ultimate, maximum density, yet not infinite. Pondering the internal structure of a black hole leads us straight to one of the deepest mysteries in modern physics: the information paradox. Stephen Hawking formulated this paradox back in the 1970s, and to this day we still don't have a universally accepted solution. Here's the crux of the issue. One of the fundamental principles of quantum mechanics states that information in the universe can never truly be destroyed. It might change its form or become incredibly scrambled, but the total amount of information must always be conserved. For example, if you burn a book, the information it contained isn't actually wiped out. Instead, it gets encoded into the motion of smoke molecules, the heat, and the light of the flame. Theoretically, by gathering all that resulting data, you could reconstruct the original text. But what happens when that book falls into a black hole? According to classical physics, once it crosses the event horizon, it vanishes from our universe forever, taking all its stored information with it. It looks like the information is simply destroyed. So what, you might ask? But for physicists, this is a catastrophe. It completely undermines the very foundations of quantum mechanics. Initially, Stephen Hawking himself argued that black holes do destroy information, a position that led to his famous wager with other leading physicists. He suggested we would simply have to rewrite our fundamental laws. However, this stance created far more problems than it solved. For instance, the disappearance of information appears to violate the law of conservation of energy. This triggered decades of fierce debate and a relentless search for a solution that could finally reconcile gravity and quantum mechanics. Ultimately, the information paradox forced physicists to fundamentally rethink the very concept of information and the nature of space-time itself. But the story didn't end there. Stephen Hawking made another groundbreaking discovery. At first, it seemed to deepen the paradox, but it ultimately may have provided the key to its resolution. He showed that black holes aren't entirely black. Due to quantum effects near the event horizon, they must slowly emit radiation. This process is now famously known as Hawking radiation. Here is how it basically works. In the vacuum of space, pairs of virtual particles and antiparticles are constantly popping into existence and immediately annihilating each other. However, if such a pair is created right at the boundary of the event horizon, one particle might fall into the black hole while its partner manages to escape. To an outside observer, this looks exactly as if the black hole emitted a particle. Crucially, to preserve the balance of energy, the particle that falls inward must possess negative energy. This results in the gradual reduction of the black hole's mass. In essence, black holes slowly evaporate over time. This process is unbelievably slow. For a black hole with the mass of the Sun, the evaporation time would be 10 to the power of 67 years. That's a 1, followed by 67 zeros, a time span vastly exceeding the current age of the universe. For a supermassive black hole like Sagittarius A star at the center of our galaxy, that time frame is even more unimaginable. But theoretically, every single black hole will eventually completely evaporate, transforming into a stream of particles. And here is where the paradox becomes critically urgent. If the black hole ultimately vanishes, what happens to all the information that fell into it? Does it simply vanish with the hole? Or is that information somehow encoded within this faint Hawking radiation? Hawking eventually reversed his position. In 2004, he publicly conceded that he had likely been mistaken and that information, after all, is not destroyed. But how does it escape? Current theoretical ideas center around the so-called holographic principle. This hypothesis suggests that all the information contained within a three-dimensional volume of space, including everything inside a black hole, can be completely described by its two-dimensional boundary. For a black hole, this boundary is its event horizon. Imagine that the information about a book falling into the black hole doesn't plunge toward the singularity. Instead, it gets imprinted onto the surface of the event horizon, forming a kind of quantum hologram. When the black hole finally evaporates, this information is slowly, piece by piece, transmitted via the outgoing particles of Hawking radiation. Thus, the information isn't lost, it simply returns to the universe in an incredibly complex and highly scrambled form. This idea sounds incredibly strange and counterintuitive. It implies that our three-dimensional perception of the world might be an illusion and that fundamental reality is actually two-dimensional. Nevertheless, the holographic principle is a key component of string theory and helps resolve many paradoxes related to black holes. While we still don't have a final definitive answer, the majority of physicists today lean toward the belief that information is indeed preserved. The only mystery remaining is the exact mechanism of its escape from that gravitational prison. Sagittarius A star, our silent neighbor, may hold the ultimate key to this fundamental secret of nature. Let's move beyond theoretical paradoxes and focus on the observable reality surrounding Sagittarius A star. The galactic center is anything but empty. It's one of the most crowded and active regions of the entire Milky Way. Star density here is millions of times greater than it is in our solar neighborhood. These stars zoom around their orbits, constantly interacting and disrupting one another. Beyond the S-stars we've already mentioned, this area is packed with other intriguing objects. For instance, in 2012, astronomers detected a gas and dust cloud dubbed G2 that was hurtling directly toward the black hole. The scientific community held its breath. Everyone anticipated witnessing the black hole tear the cloud apart and essentially eat it, triggering a powerful flare of radiation. This would have been a unique, real-time chance to study the process of accretion. However, to everyone's surprise, the G2 cloud survived its closest approach to the black hole in 2014. While it was stretched and severely deformed, it wasn't completely annihilated. This led to the hypothesis that G2 wasn't just a gas cloud, but more likely a young star cocooned in a thick, gaseous envelope. The star's own gravity helped it withstand the intense tidal forces of the black hole. This event highlighted just how complex and unpredictable the processes are in this extreme environment. The galactic center is a true laboratory where nature performs experiments with gravity, hydrodynamics, and plasma physics on scales we could never hope to replicate here on Earth. Orbiting Sagittarius. A star are not just individual stars and gas clouds, but entire star clusters as well. Right in the immediate vicinity of this supermassive black hole lies a young, massive cluster. It contains dozens of extremely hot and bright Wolf-Rayet stars. They are only a few million years old, and this presents a huge mystery. The issue is that conditions near the black hole are incredibly hostile to star formation, powerful tidal forces should rip apart any gas cloud attempting to contract and collapse into a star. So, how did these young stars get there? There are several competing hypotheses. The first relates to what's often called the youth paradox. Perhaps these stars were born far away in a much quieter region and only later migrated toward the galactic center, eventually being captured by the black hole's gravity. The second hypothesis suggests the stars did form locally, but not from a standard gas cloud. Instead, they coalesced from a dense and massive accretion disk that might have existed around Sagittarius A star in the past. This disk would have been dense enough for fragments to collapse into stars, effectively overcoming the destructive tidal forces. Which of these hypotheses is correct remains unclear. Solving this puzzle will help us better understand not only the history of our own black hole, but also the evolutionary processes of galactic nuclei in general. This demonstrates once again that every new answer we gain by studying Sagittarius A star simply generates a host of new, even more compelling questions. But what about the other black holes lurking near Sagittarius A star? Theoretical models predicted that over billions of years of gravitational interaction, a vast number of stellar mass black holes should have accumulated right in the galactic center. Since they are significantly heavier than normal stars, these black holes should have gradually sunk toward the core, forming a dense cluster around their supermassive sibling. However, for a long time, astronomers struggled to find convincing evidence of their existence. It was only recently, thanks to the analysis of data from the Chandra X-ray Observatory, that signs of an entire swarm of black holes were finally detected. Scientists specifically looked for binary systems where a black hole was actively stripping matter from a companion star. This accretion process creates intense X-ray radiation. And within a radius of just a few light-years from Sagittarius A star, roughly a dozen such bright X-ray sources were identified. Based on this limited sample, astronomers calculated that the total number of isolated black holes in this immediate region could be as high as 10,000. Alongside them, there might also be hundreds of binary systems featuring neutron stars. This finding confirms theoretical predictions and paints a picture of an even more dynamic and dangerous environment at the heart of our galaxy. Occasionally, these black holes might merge with one another or even with the supermassive black hole itself, generating powerful gravitational waves that ripple across the cosmos. Let's step back for a moment from the black hole itself and examine its broader environment. Sagittarius A star sits right at the heart of a massive structure known as the central molecular zone. This is a colossal complex of molecular clouds stretching out for hundreds of light years. It holds a massive reservoir of gas and dust, enough material to form tens of millions of stars like our Sun. Star formation processes here are significantly more active than in our own region of the galaxy, yet something is hindering this process from moving even faster. Despite the sheer abundance of this cosmic building material, the overall efficiency of star formation in this zone is surprisingly low. Scientists suspect the culprit might be the black hole itself and the activity associated with it. Powerful radiation blasting out from the accretion disk along with stellar winds from the massive stars in the central cluster can heat and accelerate these gas clouds, preventing them from collapsing to form new stars. This is an example of what is called feedback, a process where the black hole doesn't just passively consume matter, but actively dictates the evolution of its host galaxy. It effectively regulates the pace of star formation in the core regions, setting the limit on how many new stars can actually be born. Similar processes, though on dramatically larger scales, are seen in the centers of many other galaxies, where supermassive black holes use powerful jets to shut down star formation across the entire galaxy. Studying our homegrown monster helps us unlock the secrets of these crucial global cosmic processes. I wonder, has Sagittarius A star always been this quiet? Right now, it's consuming matter sluggishly, and its luminosity is extremely low, especially when you compare it to active galactic nuclei like quasars. But the data suggests that in the past, it could have been far more active and hungry. One of the primary pieces of evidence for this are the so-called Fermi bubbles. These are two gigantic structures made of high-energy particles, stretching 25,000 light-years above and below the plane of our galaxy. They were discovered in 2010 using the Fermi Gamma-ray Space Telescope. These bubbles are like the ghostly remnants of some monumental event that took place in the Milky Way's center millions of years ago. The most probable explanation for their origin is a powerful flare-up of activity from Sagittarius A star itself. Millions of years ago, our black hole might have consumed a massive gas cloud or even an entire star. This process would have created a potent accretion disk and triggered the ejection of giant jets, which then effectively inflated these bubbles. This suggests that our own galaxy was once home to an active quasar, albeit a less powerful one. For now, it's dormant, but it could certainly wake up again in the future. This whole phenomenon reminds us that galaxies are not static. They are dynamic, evolving systems, and black holes play a pivotal role in their lives, cycling between periods of intense activity and quiet slumber. The Fermi bubbles aren't the only evidence of the galactic center's tumultuous past. We have other clues. Hundreds of light-years away from Sagittarius A star, giant molecular clouds are glowing brightly in the X-ray range. This light isn't intrinsic, it's reflected. Analysis shows that these clouds are echoing X-ray radiation from an incredibly powerful flare that erupted from the galactic core just a few hundred years ago. This light echo tells us that, even on historical timescales, very recently in cosmic terms, Sagittarius A star's luminosity was 1,000,000 times higher than it is today. What caused this sudden outburst? We don't know for certain. It might have been something minor, like a small asteroid or comet falling in, or perhaps instability within the accretion disk itself. What this suggests is that our black hole's mood can change rapidly. It can shift from a quiescent, sleepy state to one of intense activity in a very short span of time. Fortunately, we are located at a safe distance. Even such a powerful flare poses no direct threat to life on Earth, but it emphasizes just how dynamic and unpredictable the environment is at the heart of the Milky Way. Our black hole isn't dead, it's merely dormant. Its past was clearly far more luminous than its present. By studying these echoes from the past, we can reconstruct the history of its life and better predict its future behavior. Let's take a step back and revisit the most fundamental question. Where do supermassive black holes actually come from? How could an object millions or even billions of times the mass of our Sun possibly form right in the heart of a galaxy? There are several leading hypotheses, and scientists are still debating which is correct, or whether multiple mechanisms might be at play simultaneously. The first hypothesis is known as the direct collapse model. This suggests that in the early universe, massive clouds of pristine gas, made primarily of hydrogen and helium, could have collapsed directly under their own gravity. Critically, they skipped the star-forming stage entirely, immediately creating a black hole tens or even hundreds of thousands of solar masses. These resulting seed black holes then grew rapidly by accreting surrounding gas and merging with other seeds. The second leading theory proposes that everything started with the universe's very first stars, the so-called population 3 stars. These stars were hundreds of times more massive than our Sun. After an incredibly short life, they collapsed into stellar mass black holes. These stellar remnants, concentrated in dense star clusters, then began to merge repeatedly, gradually building up their mass. The third hypothesis offers a middle ground. It suggests that within extremely dense stellar environments, multiple collisions and mergers of normal stars took place. This process created a single, ultramassive star, which then collapsed into an intermediate mass black hole, the perfect seed for a future galactic giant. Regardless of which mechanism proves dominant, one thing is clear. Supermassive black holes formed extremely early in the universe's history, and their growth is inextricably linked to the growth and evolution of the galaxies themselves. Sagittarius. A star is essentially our local laboratory for studying supermassive black holes, but it is far from being the biggest or even the only example of its kind. We find one of these black holes at the heart of virtually every major galaxy we observe. Their masses vary wildly, ranging from a few million solar masses like Sagittarius A star all the way up to tens of billions. The most famous giant resides in the M87 galaxy, the very object first imaged by the Event Horizon Telescope. It weighs in at 6.5 billion solar masses, but the current record holder is the black hole found at the center of the quasar TON 618. Its mass is staggering, an estimated 66 billion solar masses. This is an object that truly defies imagination. The event horizon of such a cosmic monster is so vast that dozens of our own solar systems could comfortably fit within its boundary. We observe a strong correlation between the mass of a central black hole and the properties of its host galaxy, specifically the mass and stellar velocity within its central structure, known as the galactic bulge. This correlation implies that black holes and their host galaxies grow and evolve together, mutually influencing one another. The black hole doesn't just sit passively at the core, it actively participates in galactic life, regulating star formation and shaping the galaxy's overall structure. By studying the immense variety of these cosmic leviathans, we seek to uncover the fundamental laws governing this synchronized evolution throughout the entire history of the cosmos. Let's peer far into the distant future. What will become of Sagittarius A star? It won't last forever. We've previously discussed Hawking radiation, the incredibly slow process by which black holes evaporate. In the current epoch of the universe, surrounded by plenty of gas and stars for the black hole to consume, this evaporative process is completely negligible. The mass it gains far outweighs the mass it loses, but the universe is expanding and cooling. Eventually, the stars will burn out, the gas will dissipate. An epoch will arrive when black holes are among the last massive objects remaining in the universe. At that point, the process of evaporation will become the dominant force. But we have a very, very long wait ahead. The estimated time for Sagittarius A star to completely evaporate is roughly 10 to the power of 87 years. This number is so vast it is virtually impossible to comprehend. By that time, the universe will be a cold, dark, and utterly unrecognizable place. In the final moments of its existence, the black hole's evaporation will accelerate rapidly. Once its mass shrinks to that of a small asteroid, it will detonate in a final, brilliant burst of gamma radiation, vanishing completely. Thus, at the end of time, even the most massive and longest-lived objects in the universe will cease to exist, converting into a mere cloud of elementary particles. This marks the end of the long and turbulent history of our galactic center, a quiet, solitary conclusion to a cosmic drama that spanned an unimaginable number of epochs. Could Sagittarius A star ever pose a danger to us? The answer is simple and definitive: no. We are 27,000 light-years away, residing safely within one of the galaxy's stable spiral arms. its gravitational pull on us is negligible. We don't orbit Esco A star itself. Instead, we orbit the galactic center of mass, and our trajectory is perfectly stable. In fact, even if the black hole suddenly vanished, our orbit would barely change at all. A direct threat, such as a powerful relativistic jet being fired our way, is also highly improbable. The spin axis of SGR A star, which determines the direction of these potential jets, is simply not aligned with Earth. Even if it has experienced powerful flares in the past, that radiation would be so severely attenuated by the vast distance that it couldn't possibly harm life on Earth. The only truly hypothetical yet highly improbable threat might come from a rogue star or a wandering black hole. If such an object were to pass through the solar system, it could potentially disrupt the stability of the planetary orbits. Crucially, however, this specific scenario has absolutely nothing to do with Sagittarius A star, and its probability is minuscule, so rest easy, knowing that our galactic monster is safely contained. We can continue studying it from afar, marveling at its immense power and the mysteries it holds. It is not a threat to us, but an invaluable source of knowledge about the most fundamental laws of the universe. Over the past few decades, our knowledge of Sagittarius A star has grown exponentially. So what does the future hold? Technology never stands still. The Event Horizon Telescope continues to expand. New instruments, including telescopes in space, are being connected to this global network. This will allow us to obtain even sharper and more detailed images of the black hole's shadow. Perhaps we won't just capture a static picture, but instead an actual movie showing how gas spirals around it and how hotspots appear and vanish. This will allow us to measure the black hole's parameters, such as its spin, the rate of rotation, with unprecedented accuracy. General relativity predicts that a spinning black hole should drag space-time along with it, creating an effect known as frame dragging. Measuring this effect will provide yet another rigorous test of Einstein's theory. Furthermore, the next generation of giant ground-based telescopes, like the extremely large telescope in Chile with its 39-meter mirror, will be able to track the movement of S-stars even more precisely, and perhaps they will even detect fainter objects orbiting much closer to the event horizon. Each new observation will add another crucial piece to the overall puzzle of our understanding of this astonishing object. But what about gravitational waves? Current detectors, such as LIGO and Virgo, are capable of registering the mergers of stellar mass black holes. To capture the gravitational waves generated by supermassive black holes, however, requires detectors of a vastly different magnitude. This is where the LISA project comes in, the Laser Interferometer Space Antenna. LISA will consist of a constellation of 3 spacecraft, forming a gigantic triangle in space with sides measuring 2.5 million kilometers long. These satellites will continuously exchange laser beams, measuring the distance between them with precision down to a fraction of an atom's diameter. LISA will be sensitive to the low-frequency gravitational waves generated either by merging supermassive black holes or when they devour smaller stars and black holes. If, for instance, a star or a black hole falls into Sagittarius A star, our galaxy's own central supermassive black hole, LISA will be able to register that signal. This capability will open an entirely new window onto the universe. We will be able to not merely see, but actually hear the most dramatic events unfolding in the cores of galaxies. Gravitational wave astronomy will enable us to map space-time near the event horizon and directly test the predictions of general relativity regarding the very structure of the fabric of reality. This is a future that felt like pure science fiction only a few decades ago, yet it is now firmly on the horizon. Considering Sagittarius A star, we can't help but wonder about more exotic possibilities. Some theories suggest black holes might not just be cosmic dead ends, but actual portals into other universes or to distant points in our own space-time. These hypothetical objects are known as wormholes or Einstein-Rosen bridges. It's crucial to understand that currently this is purely theoretical speculation. The classical wormholes predicted by general relativity are fundamentally unstable. They collapse so rapidly that nothing, not even light, would have time to traverse them. To make them traversable, they would require what is known as exotic matter, a hypothetical substance possessing negative energy density. We have never observed such matter, and we do not know if it can exist naturally in the universe. Therefore, Sagittarius A star is most likely not a doorway to Narnia, but exactly what it appears to be, a supermassive black hole. However, the search for answers to the most fundamental questions often begins with the boldest, most outlandish ideas. By studying the properties of real black holes, we can place constraints on these exotic theories, or, who knows, perhaps one day find a hint that the universe is structured in ways even stranger and more astonishing than we can currently imagine. The story of studying Sagittarius A star is really the story of human curiosity and ingenuity. It's a narrative about how we, tiny beings on a minuscule planet, manage to peer into the very heart of our gigantic galaxy and witness the fundamentally invisible. This was made possible by decades of meticulous, tireless work performed by thousands of scientists, engineers, and programmers worldwide. From Einstein's initial theoretical predictions to tracking the orbits of stars to building a telescope the size of our entire planet, every single step has been a seismic breakthrough pushing the boundaries of human knowledge. This story, however, is far from over. Sagittarius A star still holds countless secrets. We don't know exactly how it came into being. We still don't fully grasp how it influences its host galaxy. We don't know what truly lies beyond its event horizon or how to resolve the infamous information paradox. Yet every new answer brings us closer to understanding not just this singular object, but the fundamental laws that govern the very structure of the universe. Sagittarius A star is our cosmic sphinx, silently posing its profound riddles to humanity. And by solving them, we ultimately unlock the mystery of our own origins and our place in this vast, beautiful cosmos. So let's summarize our journey. We began by grasping the sheer scale of this invisible giant whose mass is 4 million times that of our Sun. We conceptually crossed its event horizon, the point of no return, where space and time behave in fundamentally different ways. We saw how its gravity warps light, creating bizarre optical illusions, and how it dramatically slows the very flow of time. We imagined the terrifying power of its tidal forces, strong enough to stretch any object into a thin, spaghetti-like thread. We learned how humanity, by combining telescopes across the globe, was able to capture the first ever image of this monster's shadow, confirming predictions made a century ago. We tracked the orbital dance of stars around it, which provided irrefutable proof of its existence and allowed us to precisely calculate its mass. We dove into the deepest mysteries of physics, such as the information paradox and the true nature of the singularity, concepts for which we still lack definitive solutions. We saw that Sagittarius A star is not merely a passive object, but an active player in the life of the galaxy, whose past was filled with bright flares and whose future is dictated by its slow evaporation over unimaginable eons. It serves simultaneously as a laboratory for testing fundamental theories and a crucial key to understanding the evolution of galaxies. Studying Sagittarius A star is much more than just an academic pursuit. It is part of our fundamental drive to understand the world we inhabit, our Sun, our Earth, even we ourselves. We are all parts of the Milky Way galaxy, revolving around this central object. Understanding its nature, its history, and its future is, in a profound way, understanding our own cosmic destiny. The next time you look up at the night sky toward the constellation Sagittarius, remember that hidden behind the clouds of stellar dust lies this amazing and mysterious entity. It serves as a potent reminder of how vast and intricate the universe truly is, and how much remains undiscovered and unexplained. It embodies the most extreme manifestations of the laws of physics, pushing them right to the very edge. By studying it, we expand the boundaries not only of our knowledge, but also of our imagination. We learn to think on scales involving millions of light years and unimaginable stretches of time. This journey to the heart of our galaxy is a journey to the very limits of our comprehension. And it is only just beginning. With every new discovery, the darkness at the center of the Milky Way grows a little brighter, slowly revealing more and more of its secrets. Our journey to the heart of the Milky Way now concludes. We've traveled from the visible starlight into the invisible darkness that conceals the singularity itself. We've witnessed how the elegant mathematics of relativity transforms into a physical reality capable of warping space, halting time, and ripping stars apart. Sagittarius A star is more than just an object. It represents the very frontier of our knowledge, a place where our best scientific theories collide with the ultimate unknown. Perhaps the greatest mystery it conceals isn't what lies inside, but what new laws of physics we have yet to uncover in order to fully comprehend it. It remains a silent giant, compelling us through its very existence to innovate, create new technologies, and ask ever deeper questions about the nature of reality itself. Thank you for spending this time with me, traveling through the vastness of the cosmos. I truly hope this story helped you relax and prepare for a restful sleep. If you enjoyed this journey, please subscribe to the channel and hit the like button so you don't miss future discussions on the mysteries of the universe. And now, as you begin to drift off, consider this final thought. What great cosmic mystery fascinates you above all others? Let me know your answer in the comments below. Good night, and may you have clear and peaceful dreams.